Look up at the night sky, past the familiar constellations and glittering stars, and imagine something far grander lurking just beyond what your eyes can see. Picture the Milky Way, our cosmic home, stretching across the darkness like a river of light. But hidden within this vast expanse are structures so enormous they defy comprehension, structures that shouldn't exist, yet they do. Meet the Fermi Bubbles towering above and below our galaxy like ghostly giants, each one reaching halfway across the Milky Way. These aren't just cosmic oddities. They're a puzzle that has left scientists scratching their heads for over a decade. How did these colossal bubbles form? What unleashed enough energy to create them equivalent to 100,000 exploding stars? And why do they challenge everything we thought we knew about our galaxy's quiet, orderly life? Strap in, because we're about to dive into one of the most breathtaking mysteries in modern astronomy. By the time we're done, you'll see the Milky Way in a whole new light and realize just how little we truly understand about the universe we call home. Now, let's rewind to the moment these cosmic giants first came into view. In 2010, something extraordinary caught the attention of astronomers analyzing data from the Fermi Gamma-ray Space Telescope. This powerful instrument, designed to scan the skies for high-energy gamma rays, revealed something no one had anticipated: two enormous lobes of intense radiation, each stretching 25,000 light-years upward and downward from the Milky Way's core. The discovery wasn't just surprising, it was revolutionary. Scientists, including lead researchers like Doug Finkbeiner and his team at the Harvard-Smithsonian Center for Astrophysics, were stunned. They had been mapping gamma-ray emissions across the galaxy, expecting to see a familiar, diffuse glow. Instead, they found these colossal structures, sharp-edged and symmetrical, like hourglasses of pure energy. Initial theories scrambled to explain the phenomenon. Some suggested it was the aftermath of a past eruption from Sagittarius, a star, our galaxy's supermassive black hole. Others wondered if a burst of star formation had unleashed powerful winds, carving out these bubbles. And then there were the more exotic ideas. Could dark matter annihilation be responsible? The debate was fierce, but one thing was clear: whatever created these bubbles had unleashed energy on a scale beyond anything we'd seen before. This wasn't just a new feature in our cosmic backyard, it was a wake-up call. The Milky Way, long thought to be a relatively quiet galaxy, had a violent past we were only just beginning to uncover. And with that realization, the race to solve the mystery of the Fermi Bubbles had officially begun. To truly grasp the staggering scale of the Fermi Bubbles, picture this. These towering structures stretch an astonishing 50,000 light-years from top to bottom. That's half the diameter of our entire Milky Way galaxy. If you could stand on Earth and see them with the naked eye, they would span the sky from horizon to horizon, dwarfing every star and constellation we know. Now, let's put that into perspective. Imagine our solar system, a tiny speck in this vast cosmic landscape. The bubbles are so enormous that light, the fastest thing in the universe, would take 50,000 years just to travel from one end to the other. To compare, the famous pillars of creation in the Eagle Nebula, a celestial landmark, are a mere 5 light-years tall. Even the colossal Andromeda Galaxy, our nearest galactic neighbor, spans about 200,000 light-years, meaning the Fermi Bubbles alone cover a quarter of that distance. But here's what makes them even more mind-blowing: their symmetry. These bubbles aren't chaotic or uneven. They form a near-perfect hourglass shape with crisp edges that defy expectations. It's as if some cosmic force carefully sculpted them, leaving behind a pair of gargantuan footprints in the fabric of our galaxy. And yet, despite their sheer size, they remained hidden from us until just over a decade ago. That's how vast and mysterious our universe truly is. Even structures towering over our galaxy can evade detection until the right technology comes along. The Fermi Bubbles aren't just a scientific curiosity, they're a humbling reminder of how much we still have to discover. Now, let's peel back another layer of this cosmic mystery, the gamma rays themselves. These aren't just any ordinary light emissions. We're talking about the most energetic form of light in the universe, packing a punch that defies easy explanation. When the Fermi telescope first spotted these gamma rays flooding out of the bubbles, astronomers were left scratching their heads. The intensity was unlike anything they'd seen before, and the way they were distributed smoothly spread across the bubbles rather than clustered hinted at something extraordinary happening deep within these structures. So, what makes these gamma rays so puzzling? For starters, their energy levels are off the charts. Imagine the power of 1,000 suns compressed into a single burst of light. That's the scale we're dealing with. Normally, gamma rays this intense come from violent events like supernova explosions or colliding neutron stars. But here, they're emanating uniformly from vast regions of space, suggesting a different kind of engine at work. Then there's the distribution. If the bubbles were simply remnants of a chaotic explosion, you'd expect patchy, uneven gamma-ray emissions. Instead, they're eerily symmetrical, almost as if whatever process created them is still ongoing, continuously energizing particles across the entire structure. This smoothness points to something more organized, perhaps shock waves from an ancient black hole outburst or the relentless push of high-speed particles accelerated by magnetic fields. But here's the real kicker. These gamma rays aren't just a side effect. They're a direct window into the bubble's inner workings. By studying their energy signatures, scientists can piece together how particles are being accelerated to near light speeds within the bubbles. Some theories suggest these particles might be protons slamming into interstellar gas, while others argue electrons spiraling through magnetic fields could be the culprits. Either way, the gamma rays are like cosmic breadcrumbs, leading us closer to understanding what truly powers these colossal structures. And yet, despite all we've learned, the mystery only deepens. Why do the gamma rays maintain such a consistent energy profile across vast distances? What's preventing them from dissipating or scattering over time? Each answer we uncover seems to raise new questions, reminding us that the Fermi bubbles aren't just a scientific puzzle, they're a masterclass in how much we still don't know about the forces shaping our galaxy. Now, let's turn our attention to another piece of the puzzle: observations beyond gamma rays. While the Fermi telescope revealed the high-energy heart of the bubbles, other instruments like Rossat and WMAP brought their own unique perspectives to the table, painting a fuller picture of these enigmatic structures. X-ray observations from Rossat, for instance, uncovered something fascinating. The edges of the Fermi bubbles glow with a faint but distinct X-ray signature. This wasn't just random noise, it was evidence of superheated gas, reaching temperatures in the millions of degrees. Think of it like tracing the outline of a ghostly handprint in the dark. These X-rays suggest the bubbles aren't just empty voids. They're surrounded by a shell of scorching material, likely shock-heated as the bubbles expanded outward. Meanwhile, the WMAP satellite, designed to study the cosmic microwave background, stumbled upon another clue. It detected a subtle haze of microwave radiation coinciding with the bubble's location. At first, this seemed unrelated, but scientists soon realized it could be synchrotron radiation, a telltale sign of electrons spiraling at near light speeds through magnetic fields. This hinted that the bubbles aren't just passively floating, they're alive with energetic particles dancing to the tune of invisible forces. Together, these observations filled critical gaps. The X-rays showed us where the bubbles interact with their surroundings, while the microwaves revealed the presence of accelerated particles. It's like putting together a cosmic jigsaw puzzle. Gamma rays gave us the broad strokes, but X-rays and microwaves added the fine details. They confirmed that the bubbles aren't static relics but dynamic structures, still shaping and being shaped by the galaxy around them. And here's the kicker: these multi-wavelength observations didn't just support existing theories, they challenged them. The smooth microwave haze, for example, didn't quite match predictions from pure black hole outburst models. It suggested something more complex, perhaps a mix of processes working in tandem. Every new dataset peeled back another layer, reminding us that the Fermi bubbles are more than a single mystery. They're a web of interconnected enigmas, each observation pulling us deeper into the unknown. Now let's dive into one of the most compelling explanations for the Fermi bubbles, the supermassive black hole at the heart of our galaxy. Sagittarius, a star, the colossal black hole anchoring the Milky Way, might hold the key to this cosmic mystery. Imagine a sleeping giant that occasionally wakes in a fury. Scientists suspect that millions of years ago, Sagittarius, a star, might have gone through a violent phase, devouring enormous amounts of gas and dust. As material spiraled into the black hole, it could have unleashed unimaginable energy in the form of powerful jets shooting outward at nearly the speed of light. These jets, packed with high-energy particles, might have punched through the galaxy's gas, inflating the colossal bubbles we see today. But how exactly does a black hole create structures so vast? Picture a balloon being blown up inside a dense fog. The jets act like the air rushing into the balloon, pushing aside the surrounding gas and carving out the bubble's distinct shape. The shock waves from this expansion would heat the gas to extreme temperatures, explaining the X-ray glow at the edges. Meanwhile, the high-speed particles within the jets could generate the gamma rays and microwaves we detect, tying all the observations together. This theory isn't just speculation, it's backed by evidence from other galaxies. We've seen supermassive black holes in distant galaxies producing similar enormous outflows, though none as neatly symmetrical as the Fermi bubbles. That symmetry is a puzzle in itself. If Sagittarius, a star, was the sculptor, why are the bubbles so perfectly balanced? Some researchers suggest it might have been a brief, intense outburst, like a single, powerful sneeze rather than a prolonged cough. Others think magnetic fields could have guided the jets into such a uniform shape. Yet, as convincing as this idea is, it's not without its challenges. The energy required to inflate the bubbles is staggering, equivalent to tens of thousands of supernovae exploding at once. Could Sagittarius, a star, really have been that active in the relatively recent past? And why don't we see clear signs of such a cataclysmic event in the surrounding stars and gas? These questions keep scientists digging deeper, because if the black hole is responsible, it means our quiet galactic center was once a raging powerhouse, rewriting the story of the Milky Way's past. While the black hole theory is compelling, there's another cosmic powerhouse that could explain the Fermi bubbles. A fireworks show of star birth. Picture this: millions of stars igniting in a frenzy within the galactic center, their combined energy creating a storm powerful enough to sculpt these colossal structures. When massive stars form, they don't just shine, they unleash fierce stellar winds, streams of charged particles racing outward at incredible speeds. Now, imagine not just one star, but hundreds or even thousands of these giants being born in a tight cluster over a relatively short cosmic timespan. The combined force of their winds would act like a cosmic blowtorch, pushing gas outward in opposite directions and carving out the bubbles we observe today. This scenario isn't pure imagination. We've seen starburst galaxies undergoing intense star formation where similar winds create vast outflows. The difference here is scale and symmetry. The Fermi bubbles are remarkably balanced, suggesting a coordinated event. Some scientists propose that a sudden, dramatic surge in star formation, possibly triggered by a gas cloud collapsing into the galactic center, could have produced the necessary energy. The bubble's sharp edges might then be the result of shock waves from these winds slamming into surrounding material. But like any good cosmic mystery, this theory has its skeptics. Could star formation alone generate enough energy to inflate structures 50,000 light-years tall? Calculations suggest it's possible, but barely. And why don't we see evidence of such a dramatic starburst in the stars lingering near the galactic center today? Perhaps the most massive stars from that era have already exploded, leaving behind quieter remnants. The debate continues, but one thing's certain: whether it was a black hole's fury or a stellar baby boom, the Fermi bubbles remind us that even our seemingly calm galaxy has a violent, energetic past. Now, let's venture into one of the most intriguing possibilities. What if the Fermi bubbles aren't just the work of black holes or star formation, but something far more mysterious? Imagine an invisible cosmic dance happening right above and below our galaxy, where particles we can't even see might hold the key to this puzzle. Dark matter, that elusive substance making up most of the universe's mass, could be playing a starring role. Here's how it might work. When dark matter particles collide, they could annihilate each other, releasing a burst of energy, including the very gamma rays we detect in the bubbles. Think of it like cosmic fireworks, but instead of light and sound, you get high-energy radiation lighting up the sky. This idea isn't as far-fetched as it sounds. Some theories suggest dark matter could be concentrated near the galactic center, where gravity is strongest. If these particles interact just right, their annihilation could produce enough energy to inflate the bubbles. The symmetry of the structures fits two. Dark matter would naturally distribute evenly, creating the balanced lobes we observe. But here's the catch: we've never directly detected dark matter, let alone seen it annihilate. While the math checks out, there's no smoking gun yet. Other explanations, like black hole activity or star formation, don't require unknown physics. Still, the possibility is tantalizing. If dark matter is behind the bubbles, it would be our first real clue to its behavior on a galactic scale. Of course, skeptics point out that the gamma rays could come from more ordinary sources, like fast-moving cosmic rays slamming into gas. And without direct evidence, the dark matter theory remains in the realm of what if. But that's what makes science thrilling. Sometimes the most exotic explanations push us to rethink everything we know. Whether it's dark matter or something else, the Fermi bubbles keep us guessing, and that's half the fun. Now, let's step into the heart of the scientific debate, where brilliant minds clash over the true origins of the Fermi bubbles. Picture a room full of astrophysicists, each armed with data and simulations, passionately defending their favorite theory. Is it the supermassive black hole's violent outburst, a frenzy of star formation, or the enigmatic hand of dark matter? The truth is, no one has a definitive answer yet, and that's what makes this debate so electrifying. Take, for example, the heated discussions at the International Astronomical Union Symposium in 2019. Researchers presented competing models, with some arguing that the bubble's sharp edges and symmetry point squarely to black hole activity. Others countered that star-forming regions could produce similar structures under the right conditions. Meanwhile, dark matter proponents held their ground, insisting that annihilation fits the gamma-ray patterns better than anything else. The room was divided, and the papers published afterward reflected that, each side digging in, refining their arguments. Then there's the famous 2015 study in the Astrophysical Journal, where one team claimed their simulations ruled out star formation as the primary driver. Their rivals fired back in a follow-up paper, pointing out gaps in the assumptions. It's this back and forth that drives progress. Every critique sharpens the next round of research, pushing scientists to collect better data or build more accurate models. What's fascinating is how personal these debates can get. At conferences, you'll hear phrases like, "Your model ignores the microwave haze," or "Your dark matter cross-section is unrealistic." But beneath the sparring lies mutual respect. Everyone agrees the bubbles are a game changer, they just disagree on the rules, and that's the beauty of science. When something as colossal and mysterious as the Fermi bubbles appears, it's okay not to have all the answers right away. The debate itself is a sign of a healthy, thriving field. Each theory, whether it ultimately holds up or not, brings us closer to understanding our galaxy's hidden story. So while the arguments rage on, one thing's certain: the Fermi bubbles have given astrophysics one of its most exciting puzzles yet. Now, let's travel back in time to uncover when these colossal structures first emerged. Scientists estimate the Fermi bubbles formed between 2 and 4 million years ago, a blink of an eye in cosmic terms. To put that into perspective, this was around the same time early ancestors of humans were just beginning to walk upright on Earth. But what was happening in our galaxy during this era? Picture the Milky Way center, a bustling hub of activity. Sagittarius, a star, the supermassive black hole at our galaxy's heart, may have been in the midst of a violent outburst, spewing jets of energy that inflated the bubbles. Alternatively, a burst of star formation could have unleashed powerful stellar winds, carving out these immense structures. Either way, the event would have been spectacular, a cosmic eruption lighting up the galactic core. This period wasn't just dramatic for the Milky Way center. The energy released would have rippled outward, affecting nearby stars and gas clouds. Imagine shockwaves racing through space, heating interstellar material and potentially triggering or disrupting new star formation. Some researchers even speculate that the bubbles formation could have influenced the orbits of stars close to the galactic center, sending them on new trajectories. Interestingly, this timeline aligns with other clues from our galaxy's history. Observations of nearby stars reveal traces of past radiation events, hinting that something monumental occurred around the same time the bubbles formed. It's like piecing together a cosmic crime scene. Each clue brings us closer to understanding what really happened millions of years ago. While we can't witness this event directly, the Fermi bubbles serve as a fossil record of the Milky Way's explosive past. They remind us that our galaxy is anything but static. It's a dynamic, ever-changing arena where colossal forces shape its evolution. And as we continue to study these mysterious structures, we uncover more about the dramatic history written across the cosmos. Now, shifting our focus to the very shape of these cosmic giants, the Fermi bubbles reveal a striking symmetry that's hard to ignore. Picture an enormous hourglass stretching above and below the Milky Way center, each half mirroring the other with near-perfect precision. This symmetry isn't just visually stunning, it's a critical clue about the forces that sculpted them. What's even more fascinating are their sharp, well-defined edges. Unlike fuzzy cosmic clouds or diffuse gas halos, the bubbles' boundaries are remarkably crisp, almost as if they were carved with a knife. This clarity challenges some of our earlier formation theories. For instance, if the bubbles were created by slow, steady processes like gentle stellar winds, we'd expect their edges to be more blurred and uneven. But these razor-sharp borders suggest something far more violent, a sudden, explosive event, like a colossal outburst from the supermassive black hole at our galaxy's core. The hourglass shape itself adds another layer of intrigue. It hints at a powerful, focused energy release, possibly channeled by magnetic fields or directed jets. Some simulations show that such a structure could form if a burst of energy shot out perpendicular to the galactic disk, inflating the bubbles like balloons pinched at the center. Yet, other models struggle to replicate this precise morphology, leaving scientists to wonder if we're missing a piece of the puzzle. These structural details aren't just academic curiosities, they're fingerprints of the event that created the bubbles. Every curve, every sharp edge tells a story about the energy, the environment, and even the timing of that ancient cataclysm. And as we piece together these clues, we get closer to understanding not just the bubbles, but the dynamic, sometimes violent life of our galaxy. Now, let's talk about the sheer power behind these colossal structures. The energy required to inflate the Fermi bubbles is almost beyond comprehension, equivalent to the explosive force of 100,000 supernovae. To put that into perspective, a single supernova can outshine an entire galaxy for weeks. Now imagine multiplying that by 100,000. That's the kind of raw, unfathomable energy we're dealing with here. So, what cosmic event could possibly unleash such a staggering amount of power? The leading suspect is our galaxy's supermassive black hole, Sagittarius, a star. When black holes feed on surrounding gas and dust, they don't just quietly snack, they can erupt in violent outbursts, shooting jets of energy at nearly the speed of light. If Sagittarius, a star, had a particularly voracious meal millions of years ago, the resulting explosion could have pumped enough energy into space to carve out the bubbles we see today. But there's another contender, a frenzy of star formation in the galactic center. When massive stars are born in huge numbers, their fierce winds and eventual supernova can combine into a galactic-scale energy storm. Picture thousands of stars, each blasting out radiation and stellar winds, collectively pushing gas outward with enough force to create these enormous structures. And then there's the wild card, dark matter. While it's a long shot, some theories suggest that if dark matter particles collided and annihilated near the galactic center, the energy released could match what we see in the bubbles. It's a tantalizing idea, though one that's much harder to prove. Whatever the source, one thing is clear: the Fermi bubbles are a testament to the titanic forces at work in our galaxy. They remind us that even in the vast quiet of space, violence and beauty often go hand in hand. Now, let's shift our gaze to another fascinating piece of this cosmic puzzle, the Fermi haze. This mysterious, fog-like glow of gamma rays blankets the center of our galaxy, almost like an ethereal backdrop to the towering Fermi bubbles. At first glance, it might seem unrelated, but scientists have uncovered intriguing connections that suggest these two phenomena could be part of the same grand event. The haze stretches across the galactic plane, overlapping with the bases of the bubbles, and shares a similar energy signature. This has led researchers to wonder, could the haze be the remnants of whatever outburst created the bubbles? Imagine a massive explosion at the heart of the Milky Way. The initial blast might have carved out the bubbles, while leftover energy and particles settled into a diffuse glow, creating the haze we detect today. But there's a twist. Some studies argue the haze might have a different origin, like the collective radiation from countless cosmic rays or even the decay of dark matter. If that's the case, the overlap with the bubbles could just be a cosmic coincidence. Yet, the symmetry of both structures centered on Sagittarius, a star, hints at a deeper link. The debate continues, but one thing is certain: whether they're siblings or distant cousins, the Fermi bubbles and the Fermi haze together paint a vivid picture of our galaxy's dynamic and sometimes violent history. Unraveling their connection could bring us closer to understanding the hidden forces shaping the Milky Way. Now, let's consider the ripple effects these colossal structures have on their cosmic neighborhood. The Fermi bubbles aren't just passive features, they're dynamic forces reshaping the galactic environment around them. Picture them as massive shock waves, pushing and sculpting the gas clouds that drift near the Milky Way center. These clouds, the raw material for new stars, get compressed or scattered by the bubble's energy, potentially altering the rhythm of star formation in their vicinity. But the influence doesn't stop there. Cosmic rays, those high-energy particles racing through space, might also get a boost from the bubbles. Some researchers suggest the bubbles act like natural particle accelerators, hurling cosmic rays across the galaxy. If that's true, these rays could travel far beyond the bubbles, even reaching Earth's neighborhood, though don't worry, they're far too faint to affect us. Then there's the question of heat. The bubble's intense radiation could be warming the surrounding gas, making it harder for stars to form. Imagine a cosmic oven, gently simmering the galaxy's star-forming fuel. On the flip side, the turbulence they create might also trigger pockets of star birth in unexpected places. It's a delicate balance, and scientists are still piecing together how these opposing forces play out. One thing's clear: the Fermi bubbles are more than just a spectacle. They're active players in the Milky Way's ongoing story, shaping its structure and evolution in ways we're only beginning to understand. Every new observation brings us closer to unraveling their full impact on our galactic home. Now, let's step outside our galaxy for a moment and see how the Fermi bubbles stack up against similar structures elsewhere in the cosmos. It turns out the Milky Way isn't the only galaxy sporting these enormous energetic features. Take M87, for example, a giant elliptical galaxy with its own set of colossal bubbles, powered by a supermassive black hole even more active than our own Sagittarius, a star. What's fascinating is how these bubbles, despite appearing in different types of galaxies, share striking similarities. Both the Fermi bubbles and M87 structures are shaped by high-energy processes likely tied to their central black holes. But here's where the differences emerge. M87's bubbles are more pronounced, stretching tens of thousands of light-years and glowing brightly in radio waves, a testament to its black hole's extreme activity. In contrast, our Fermi bubbles are subtler, detected primarily in gamma rays, hinting at a quieter, perhaps more ancient outburst. Then there's Centaurus A, another galaxy with bubble-like lobes filled with fast-moving particles. These lobes are thought to be the result of repeated black hole eruptions over millions of years. Comparing them to the Fermi bubbles raises an intriguing question. Are we seeing different stages of the same phenomenon or entirely distinct cosmic events? What ties all these structures together is the underlying physics. Whether it's the Milky Way, M87, or Centaurus A, the bubbles seem to be signatures of black hole activity, star formation bursts, or even dark matter interactions. Studying them side by side helps astronomers piece together a universal playbook how galaxies grow, evolve, and interact with their surroundings. So, while the Fermi bubbles are unique to our home galaxy, they're part of a much larger cosmic family. By understanding their relatives, we get closer to unlocking the secrets of how galaxies breathe, erupt, and shape the universe around them. Now, let's dive into the digital realm where scientists are using supercomputers to recreate these cosmic giants in virtual space. Simulations play a crucial role in testing how the Fermi bubbles might have formed, allowing researchers to tweak variables and compare results with real observations. Imagine running countless experiments without waiting millions of years. Supercomputers make it possible. One of the biggest breakthroughs came when simulations successfully replicated the bubble's sharp edges and symmetrical structure. Early models struggled to explain why the boundaries are so well defined, but by incorporating powerful jets from Sagittarius, a star, scientists finally matched what telescopes see. These virtual experiments suggest that a brief but intense outburst from our galaxy's black hole could have inflated the bubbles in just a few million years. Another key insight from modeling is the role of magnetic fields. Simulations show that without strong magnetic fields shaping the outflow, the bubbles would look more like chaotic splashes rather than the elegant hourglass we observe. This discovery points to magnetic forces acting as cosmic sculptors, guiding high-energy particles into the bubble's distinct form. Interestingly, some simulations also explore alternative origins like starburst winds or dark matter collisions. While these models can produce bubble-like structures, they often fail to match the exact energy distribution seen in gamma-ray data. This mismatch helps narrow down the possibilities, steering the debate toward black hole activity as the leading explanation. The beauty of these simulations lies in their ability to bridge theory and observation. By virtually testing different scenarios, scientists can refine their understanding of not just the Fermi bubbles, but galaxy-scale outflows across the universe. Each digital breakthrough brings us closer to solving the mystery of these colossal structures, one line of code at a time. Now, let's shift our focus to the real-world hurdles scientists face when trying to study these enigmatic structures. Observing the Fermi bubbles isn't as straightforward as pointing a telescope at the night sky. It's like trying to spot a faint whisper in a roaring concert. One of the biggest challenges is their incredibly dim emissions. The gamma rays we detect are just a whisper against the backdrop of the Milky Way's brighter signals, requiring ultra-sensitive instruments to pick them out. Adding to the difficulty is our unfortunate vantage point. We're stuck inside the galaxy, looking at it edge-on, which means the bubbles are seen sideways rather than face-on. Imagine trying to study a giant hourglass by peering through its narrow, wasted tuft to get a clear picture of its full shape and structure. This perspective makes it harder to map their boundaries or understand how they connect to the galactic center. Then there's the issue of cosmic noise. The Milky Way is bustling with other high-energy phenomena, from pulsars to supernova remnants, all emitting gamma rays that can muddy the data. Teasing out the bubble-specific signals from this cosmic cacophony is like isolating a single instrument in a symphony. Even advanced filtering techniques can only do so much, leaving room for uncertainty in the observations. Weather in space doesn't help either. Interstellar gas and dust scatter and absorb some of the emissions, further dimming the already faint signals. It's like trying to see through fog. The more layers there are, the harder it is to discern the details. Despite these obstacles, scientists keep pushing the limits of technology and creativity to uncover the bubble's secrets. Every new observation, no matter how challenging, brings us one step closer to understanding these colossal enigmas hovering above and below our galaxy. Looking ahead, the next generation of telescopes promises to shed even more light on the mysteries of the Fermi Bubbles. One of the most exciting tools on the horizon is the Cherenkov Telescope Array, a cutting-edge observatory designed to detect gamma rays with unprecedented precision. Unlike current instruments, this array will capture higher-resolution images of the bubble's structure, helping scientists pinpoint the exact sources of their emissions. It's like upgrading from a blurry snapshot to a high-definition video. Suddenly, details that were once invisible come into sharp focus. Beyond this, several proposed missions are being developed with the Fermi Bubbles in mind. Imagine spacecraft equipped with specialized detectors orbiting above Earth's atmosphere to avoid interference, dedicated solely to studying these colossal structures. These missions aim to map the bubbles in multiple wavelengths simultaneously, combining gamma-ray, X-ray, and radio data to paint a fuller picture. Think of it as assembling a cosmic jigsaw puzzle where every piece reveals a new clue about their origins. Meanwhile, advancements in computational modeling are set to play a crucial role. Supercomputers will simulate different formation scenarios, testing whether black hole outbursts, star formation surges, or even dark matter collisions best explain the bubble's properties. These virtual experiments could narrow down the possibilities, guiding future observations toward the most promising leads. The future of Fermi bubble research isn't just about bigger telescopes, it's about smarter, more targeted approaches. With each technological leap, we move closer to unraveling one of the Milky Way's most spectacular secrets. And who knows, the answers might rewrite our understanding of galactic evolution itself. Now, here's something truly exciting. You don't need a PhD or access to a giant telescope to help uncover the secrets of the Fermi Bubbles. Amateur astronomers and citizen scientists around the world are playing a vital role in this cosmic detective work. Thanks to open access data from telescopes like Fermi, anyone with a computer and curiosity can dive into the hunt for gamma-ray clues. Projects like Zooniverse's Gamma-Ray Hunters let volunteers sift through real telescope data, flagging unusual patterns or emissions that might hold the key to understanding these mysterious structures. Think of it like a galactic treasure hunt. Professional researchers simply don't have the bandwidth to analyze every single data point, so they rely on the collective power of thousands of eyes scanning the information. And here's the cool part: amateurs have already made discoveries, spotting faint gamma-ray features that automated algorithms missed. It's a perfect example of how science is becoming more collaborative, breaking down the walls between experts and enthusiasts. Beyond data analysis, citizen scientists can also contribute by monitoring the Milky Way's center with backyard telescopes. While gamma rays are invisible to the naked eye, tracking changes in visible light or radio waves near the bubble's base can provide valuable context. Online communities share observations, pooling their findings to create a richer, real-time picture of our galaxy's activity. So whether you're a seasoned stargazer or just someone who loves a good mystery, there's a place for you in Fermi bubble research. Who knows, the next big breakthrough might come from a curious mind clicking through data on their laptop, proving that sometimes the most profound discoveries start with everyday people looking up and asking, what's really going on out there? Now, let's step into the world of art and imagination, where the Fermi bubbles take on a life beyond raw data. Scientists aren't the only ones captivated by these cosmic giants. Artists and visual storytellers have transformed them into breathtaking works that bridge the gap between complex astrophysics and public wonder. Picture this: luminous, swirling towers of light stretching from the Milky Way's core, rendered in vivid colors that make the invisible gamma rays tangible. These artistic interpretations aren't just pretty pictures, they're powerful tools that help us grasp the scale and mystery of structures too vast to photograph directly. Take, for example, the digital visualizations created by NASA's conceptual art team. By combining real telescope data with artistic license, they've produced animations that let us fly through the bubbles, revealing their hourglass shape and towering height in ways graphs and equations never could. Museums and planetariums often feature these visuals, turning abstract science into immersive experiences that spark curiosity in visitors of all ages. But it's not just about accuracy. Art also invites emotion. Paintings and sculptures inspired by the bubbles explore themes of cosmic violence and beauty, like a recent exhibit that depicted them as celestial geysers frozen mid-eruption. Such works remind us that science and creativity aren't opposites, they're partners in storytelling. When a child gazes at a glowing illustration of the bubbles, they might not understand particle physics, but they'll feel the awe of our dynamic universe. Even educational platforms leverage this synergy. YouTube channels and science blogs use animated breakdowns where the bubbles inflate over time, simplifying their formation theories into engaging narratives. By blending cutting-edge research with compelling visuals, artists and communicators ensure that the Fermi bubbles aren't locked away in academic papers. They're alive in our collective imagination, inspiring the next generation of scientists and dreamers alike. So the next time you see a stunning space artwork, look closer. Behind those brushstrokes or pixels might just be a cosmic mystery waiting to be understood and felt. Now let's turn back the cosmic clock and explore the Milky Way's explosive past. The Fermi bubbles aren't the first signs of chaos in our galaxy's history, far from it. In fact, the bubbles fit into a long legacy of violent outbursts that have shaped the galaxy we see today. Evidence suggests our galactic center has been anything but quiet. Take the so-called Fermi haze, a faint glow of gamma rays that blankets the inner Milky Way. This haze might be the ghost of an even older eruption, one that happened millions of years before the bubbles formed. Then there are the giant gas clouds near the galactic center, some of which show signs of being violently pushed outward, as if caught in the wake of a past explosion. But the story doesn't stop there. Look beyond our galaxy and you'll find clues in others. Galaxies like Messier 87 and Centaurus have their own versions of Fermi bubbles, towering structures carved out by their supermassive black holes. These cosmic cousins suggest that outbursts like the one that created our bubbles aren't rare, they're part of a galactic cycle, a recurring drama playing out across the universe. So what does this mean for the Milky Way? If our galaxy has erupted before, it could erupt again. Some researchers speculate that another outburst might happen in the distant future, sending fresh waves of energy through the galaxy. For now, though, the Fermi bubbles stand as a reminder our home in the cosmos is far from peaceful, and its past is written in bursts of light and energy we're only beginning to decode. As we piece together this turbulent history, one thing becomes clear: the bubbles aren't just a scientific curiosity. They're a chapter in an epic story, one that stretches back millions of years and will continue long after we're gone. Now, let's shift our perspective and consider how modern astronomy is tackling the Fermi Bubbles puzzle from multiple angles. The key to unlocking their secrets might not lie in a single type of observation, but in combining different cosmic messengers, a technique known as multi-messenger astronomy. Think of it like piecing together a jigsaw puzzle where each piece comes from a different wavelength of light or even a different type of particle. Gamma rays detected by the Fermi telescope gave us the first glimpse of the bubbles. But gamma rays alone can't tell us everything. That's where X-rays come in. Observations from telescopes like Chandra reveal hot gas and shock waves within the bubbles, helping us map their structure in finer detail. Then there's radio waves. Instruments like the Very Large Array have spotted faint radio emissions tracing the edges of the bubbles, possibly hinting at magnetic fields or accelerated particles. And let's not forget neutrinos, those ghostly particles that barely interact with matter. If detectors like IceCube could catch neutrinos coming from the bubbles, it would be a smoking gun for particle acceleration happening inside them. By stitching together data from all these sources, astronomers can build a more complete picture. For example, gamma rays might tell us where high-energy particles are colliding, while X-rays show us the hot gas they're heating up. Radio waves could reveal how magnetic fields shape the bubbles, and neutrinos might confirm whether dark matter plays a role. It's a cosmic detective story where every clue matters. This approach isn't just about collecting more data. It's about seeing the bubbles in a whole new light. Each messenger brings a unique piece of the puzzle, and together they could finally reveal what's powering these colossal structures. The next breakthrough might come from connecting the dots across the electromagnetic spectrum and beyond, turning the Fermi bubbles from a mystery into a masterpiece of cosmic understanding. Now, let's turn our attention to another fascinating piece of the Fermi Bubbles puzzle, the role of magnetic fields. These invisible forces might be the hidden architects shaping these colossal structures and controlling the high-energy particles inside them. Magnetic fields are like cosmic highways guiding charged particles along their paths. Within the Fermi Bubbles, these fields could be the reason for their sharp, well-defined edges. Imagine blowing soap bubbles. Surface tension keeps them smooth and round. In a similar way, magnetic fields might act like a cosmic skin, containing the bubbles and preventing them from dissipating into the surrounding space. But how do we even detect these invisible fields? Astronomers look for clues in polarized light and radio emissions. When charged particles spiral around magnetic field lines, they emit a specific type of radio wave that can reveal the field's strength and direction. Observations from radio telescopes suggest the bubble's edges might be threaded with these magnetic structures, acting like giant particle accelerators. Here's where it gets even more interesting. These magnetic fields could be supercharging particles to extreme energies. Just like a slingshot, the fields might fling electrons and protons to near light speeds, producing the gamma rays we observe. Some theories even suggest that the bubble's magnetic environment could be so intense that it mimics the conditions around black holes, creating natural cosmic laboratories for particle physics. Yet mysteries remain. Are these magnetic fields leftovers from the original event that formed the bubbles, or are they constantly being regenerated by turbulent gas flows? And how do they interact with the Milky Way's larger magnetic framework? Answering these questions could unlock new insights into not just the bubbles, but the very fabric of our galaxy. As we piece together the magnetic story of the Fermi bubbles, one thing becomes clear: these fields are more than just invisible lines in space. They're dynamic forces shaping some of the most energetic phenomena in our galaxy, and understanding them might just be the key to solving the bubble's biggest secrets. Now, let's shift our gaze from the magnetic forces shaping the Fermi bubbles to another electrifying possibility. Could these colossal structures be firing cosmic rays toward Earth? Cosmic rays are high-energy particles, mostly protons and atomic nuclei, that zip through space at nearly the speed of light. They constantly bombard our planet, but their origins have long puzzled scientists. Some of the most energetic cosmic rays might actually trace back to the Fermi bubbles. Think of the bubbles as a giant cosmic particle accelerator, far more powerful than anything humans could build. Here's how it could work. The turbulent environment inside the bubbles, combined with their intense magnetic fields, might act like a natural slingshot. Charged particles get trapped, whirled around, and ejected with mind-blowing energy. If these particles escape the bubbles, they could travel across the galaxy, eventually reaching Earth. But how do we connect these dots? Scientists look for telltale signatures in the cosmic rays we detect. Some high-energy particles match the expected profile of those accelerated in environments like the bubbles. However, it's a cosmic detective story. Other sources, like supernova remnants, also produce similar particles. What makes the Fermi bubbles special is their sheer scale. The energy required to produce the gamma rays we see suggests they could also be generating ultra-high-energy cosmic rays. If confirmed, this would rewrite our understanding of where these mysterious particles come from. Yet the puzzle isn't solved. Cosmic rays don't travel in straight lines, they zigzag through interstellar magnetic fields, making it tough to trace their origins. Plus, the bubbles are far away and their signals get mixed with other galactic noise. Future detectors, like the Cherenkov telescope array, might finally crack this case by pinpointing cosmic rays back to their sources. So, while we can't say for certain yet, the Fermi bubbles remain a prime suspect in the cosmic ray mystery. Unraveling this connection wouldn't just solve a decades-old question, it would reveal how these enormous structures shape the entire galaxy, right down to the particles raining on our planet. Now, let's peel back another layer of the Fermi bubbles mystery by examining the light they emit. Not all radiation is created equal, and the bubbles produce both thermal and non-thermal emissions. Understanding this difference is like having a decoder ring for their hidden secrets. Thermal emissions come from hot gas, where particles collide and release energy simply because of their temperature. Think of it like a stove burner glowing red. The hotter it gets, the more light it gives off. In the Fermi bubbles, thermal X-rays detected by telescopes like Rosat suggest there's superheated gas, possibly heated by shock waves from whatever event created the bubbles. This tells us about the physical conditions inside these structures, like their temperature and density. On the other hand, non-thermal emissions are far more exotic. These don't come from heat but from high-energy particles zipping through magnetic fields or colliding. The gamma rays that first revealed the bubbles are a prime example. They're produced when electrons, accelerated to near light speeds, slam into lower-energy photons, or when cosmic rays interact with gas. This non-thermal signature points to extreme processes, particle acceleration on a galactic scale. Here's why this duality matters. Thermal emissions paint a picture of the bubble's environment, like a snapshot of their weather. Meanwhile, non-thermal emissions expose the frenetic particle physics happening within them. Together, they suggest the bubbles aren't just static structures but dynamic engines, where energy is constantly being transferred and transformed. But there's a twist. The balance between these emissions challenges theorists. If the bubbles were powered solely by a black hole outburst, we'd expect certain thermal signatures that aren't always there. Conversely, if star formation were the culprit, the non-thermal gamma rays might be harder to explain. This mismatch keeps scientists debating and searching for better models to reconcile both types of radiation. By studying this interplay, astronomers get clues about the bubble's power source, age, and even their impact on the galaxy. Next time you hear about gamma rays or X-rays from space, remember, each type of light tells a different part of the story, and the Fermi bubbles are whispering in both languages. Now let's shift our perspective and consider the Fermi bubbles from a different angle, not just as cosmic structures, but as colossal natural laboratories. These bubbles might be acting like the universe's own particle accelerators, dwarfing anything humans have built on Earth. Think of the Large Hadron Collider, the most powerful particle accelerator we've created. It smashes particles together at nearly the speed of light to uncover the secrets of matter. The Fermi Bubbles could be doing something similar, but on a scale that's almost unimaginable. Inside these vast structures, magnetic fields and shock waves may be accelerating particles to energies far beyond what our most advanced machines can achieve. Here's how it works. The bubbles are filled with turbulent magnetic fields, twisted and stretched by the forces that shape them. Charged particles like electrons and protons get caught in these fields and whipped around, gaining tremendous energy, just like a surfer riding an endless wave. When these particles finally collide with gas or light, they release the gamma rays we detect. It's a natural version of what happens in our colliders, but with energies that could help us understand some of the most extreme physics in the universe. What makes this even more fascinating is the sheer power involved. The bubbles don't just accelerate particles, they do it continuously across tens of thousands of light years. If we could tap into even a fraction of that energy, it would revolutionize our understanding of high-energy physics. But there's a catch. Unlike our controlled experiments on Earth, the bubbles are chaotic and unpredictable. Scientists are still piecing together how these natural accelerators operate and whether they can teach us about phenomena like dark matter or cosmic rays. One thing's for sure, the Fermi bubbles are more than just pretty structures. They're active, dynamic engines pushing the limits of what we know about particle physics. So next time you hear about breakthroughs from particle colliders, remember the universe might have been running its own experiments long before we even existed. And the Fermi bubbles could be one of its most impressive creations. Now, let's peel back another layer of the Fermi bubbles' mystery by examining their chemical makeup. The clues lie in the light they emit specifically, the spectral lines that act like cosmic fingerprints. These lines reveal whether the material inside the bubbles is pristine gas from the early universe or recycled debris from dying stars. When scientists analyze these spectral signatures, they're looking for telltale elements like iron, oxygen, and silicon. If the bubbles are filled with heavy elements, it suggests the material was forged in the hearts of stars and blasted out by supernova or black hole activity. On the other hand, if the composition leans toward lighter elements like hydrogen and helium, it could mean the bubbles contain untouched primordial gas, a relic from the Milky Way's infancy. Here's where it gets intriguing. Recent observations show a mix of both. Some regions within the bubbles display the chemical hallmarks of stellar processing. Think of it as cosmic recycling. Other areas, particularly toward the outer edges, show a purer, lighter composition. This duality hints at a complex origin story, where multiple forces might have shaped the bubbles over millions of years. One compelling theory is that the bubbles' material started as stellar wind or supernova debris, enriched with heavy elements but mixed with surrounding primordial gas as it expanded. This would explain the hybrid signature we see today. It's like finding layers in a geological formation. Each tells a different chapter of the story. Understanding this chemical tapestry isn't just academic. It helps us piece together the bubbles' history and their impact on the galaxy. For instance, if the material is mostly stellar in origin, it could mean the bubbles were forged during a violent episode of star formation or black hole activity. If primordial gas dominates, it might point to a quieter, more gradual process. Either way, these spectral clues are like pages in a galactic diary, helping us decode events that shaped the Milky Way long before Earth existed. And with every new observation, we get closer to reading the full story. Now, shifting our gaze to where the Fermi bubbles meet the Milky Way's disk, we uncover a fascinating interplay of forces. The bases of these colossal structures aren't just floating in isolation, they're deeply intertwined with the dense, star-filled plane of our galaxy. This boundary zone is where the bubble's high-energy material collides with the cooler, more turbulent gas of the galactic disk, creating a cosmic tug-of-war. Picture it like a storm front meeting the ocean. The bubble's hot, fast-moving particles slam into the denser disk material, generating shock waves that ripple outward. These shocks can heat the surrounding gas, trigger new star formation, or even disrupt existing clouds. It's a dynamic interface where two very different environments, each with its own physics, clash and coexist. One of the most striking features here is the bubble's sharp edges. Unlike a fading mist, their boundaries are remarkably well defined, suggesting something is containing them. Scientists suspect magnetic fields play a bouncer-like role, corralling the bubble's material and preventing it from diffusing into the disk. These invisible magnetic lines might act like a cage, shaping the bubbles and maintaining their crisp silhouette against the galactic backdrop. But the interaction isn't one-sided. The disk pushes back too. Gravitational forces and pressure from the disk's gas can compress the bubble's lower regions, altering their structure over time. Some theories even suggest that this boundary zone acts as a particle accelerator, funneling energy back into the galaxy and influencing cosmic ray populations near Earth. What makes this dance especially intriguing is its asymmetry. The bubbles don't connect to the disk uniformly. Some regions show more intense activity while others appear quieter. This unevenness hints at past events like a black hole outburst or starburst episode that might have been lopsided, leaving an imprint in how the bubbles anchor to the galaxy today. By studying this cosmic handshake, astronomers gain clues about the Milky Way's energy balance. How much heat and radiation do the bubbles inject into the disk? Do they stifle or stimulate star birth? Each answer peels back another layer of the galaxy's ongoing evolution, showing us that even structures towering 50,000 light-years tall are still tethered to the bustling streets of the galactic plane below. Now, let's turn our attention to a question that might seem surprising at first. Can these enormous Fermi bubbles change over time? And if so, what would that mean for our understanding of the galaxy? Given their staggering size, you'd expect any shifts to unfold over millions of years, far beyond human observation. But here's where things get interesting. Recent studies have begun probing whether the bubbles exhibit even subtle changes on much shorter timescales, perhaps decades or centuries. While we can't watch them evolve in real time, astronomers compare observations taken years apart, looking for shifts in gamma-ray brightness or slight alterations in their structure. Imagine it like comparing old and new photos of a distant mountain. You're searching for tiny differences that hint at movement or activity beneath the surface. So far, the evidence is inconclusive, but the implications are thrilling. If the bubbles were found to vary even slightly over human timescales, it would suggest they're not just static relics of a past explosion, but might still be actively fed by ongoing processes near the galactic center. Picture a volcano that isn't just dormant but occasionally rumbles to life, releasing fresh energy into the system. This could mean Sagittarius, a star, the Milky Way's central black hole, isn't as quiet as we thought and might still be flickering with sporadic outbursts. Alternatively, if the bubbles prove completely stable over centuries, it would reinforce the idea that they're fossils of a single cataclysmic event, a dramatic eruption that occurred millions of years ago and then faded into the cosmic background. Either way, tracking their variability helps us distinguish between these scenarios, offering clues about how often our galaxy experiences such energetic upheavals. The challenge, of course, is that these changes would be incredibly subtle. Detecting them requires ultra-precise measurements across years of data, a task made even harder by the fact that we're viewing the bubbles edge-on, like trying to spot ripples on a pond from the side. Future telescopes with sharper resolution and longer monitoring campaigns might finally settle the debate. What's at stake isn't just academic. If the bubbles are still evolving, it means our galaxy's core could be more dynamic than we realize, with potential ripple effects for nearby stars, gas clouds, and even cosmic rays reaching Earth. Time, as always, holds the answers, and with patience and better tools, we might soon catch the Fermi bubbles in the act of change. Now, let's venture into some of the more unconventional ideas floating around the Fermi bubbles theories that push the boundaries of what we think we know about our galaxy. While the leading explanations focus on black holes or star formation, a handful of scientists have proposed even wilder possibilities that could rewrite the rules of astrophysics. One such idea involves modified gravity, a radical rethinking of how gravity works on cosmic scales. Some researchers suggest that the bubbles might not be the result of explosive events at all, but rather a sign that gravity behaves differently near the galactic center than we've assumed. In this scenario, the bubbles could be a kind of gravitational echo, revealing hidden laws of physics that only kick in under extreme conditions. It's a long shot, but if true, it would revolutionize our understanding of the universe. Then there's the tantalizing possibility of primordial black holes, hypothetical remnants from the very early universe, smaller than stellar black holes but far more numerous. Could a swarm of these ancient objects lurking near the Milky Way center have collided or evaporated, releasing the energy needed to inflate the bubbles? It's a fringe theory, but one that ties into bigger questions about dark matter and the origins of the cosmos. Of course, these alternatives come with major challenges. Modified gravity struggles to explain the bubble's sharp edges and symmetrical shape, while primordial black holes remain purely theoretical. No direct evidence of their existence has been found yet. But that's the beauty of science. Even the most out-there ideas force us to test, question, and refine our models. What's fascinating is how these theories, however speculative, highlight just how much we still don't understand about the Fermi bubbles. They remind us that the universe loves to surprise us, and sometimes the answers lie not in tweaking existing ideas, but in daring to imagine entirely new ones. As observations improve, even the wildest hypotheses might find unexpected support, or crumble under scrutiny, leaving us with fresh mysteries to solve. Now, let's shift our focus to the classroom, because the Fermi bubbles aren't just reshaping our understanding of the galaxy, they're also transforming how we teach astronomy. These colossal structures have become a cornerstone in modern astrophysics education, offering students a front-row seat to the dynamic and sometimes unpredictable nature of scientific discovery. Just a decade ago, textbooks painted a relatively static picture of the Milky Way, focusing on its spiral arms, central black hole, and star-forming regions. But the discovery of the Fermi bubbles forced educators to rewrite entire chapters. Suddenly, students weren't just learning about the galaxy's anatomy. They were grappling with an unsolved mystery, one that challenges even the most established theories. Universities have quickly adapted, incorporating the bubbles into courses on high-energy astrophysics and galactic evolution. Professors use them as a case study to show how new observations can upend old assumptions. Imagine being an astronomy student today, analyzing real gamma-ray data from the Fermi telescope, debating whether the bubbles were carved by a black hole eruption or a burst of star formation. It's science in action, not just memorized facts. Even at the high school level, the bubbles are making waves. Simplified models and visualizations help younger students grasp their mind-bending scale, 50,000 light-years tall, dwarfing everything else in our galaxy. Teachers use them to spark curiosity, asking questions like, what else might be hiding in plain sight? Or how many more cosmic surprises are waiting to be found? Beyond traditional classrooms, the bubbles have become a favorite topic in public science outreach. Planetarium shows, YouTube explainers, and even science festivals feature them as a prime example of how cutting-edge research unfolds. They've turned abstract concepts like gamma rays and galactic winds into something tangible and thrilling. What's truly remarkable is how the Fermi bubbles embody the spirit of science itself, a reminder that our knowledge is always evolving. They teach the next generation not just about the universe, but about the process of discovery, the excitement, the debates, and the humility of realizing how much we still have to learn. And that's a lesson no textbook could ever fully capture until now. But beyond the textbooks and telescopes, the Fermi bubbles invite us to step back and reflect on something deeper: our place in this vast, ever-changing cosmos. These colossal structures aren't just scientific curiosities, they're humbling reminders of how much we still don't understand about the universe we call home. Think about it. For centuries, humanity saw the Milky Way as a stable, almost orderly system. Now, we're staring at evidence of violent, galaxy-shaping events that occurred just a few million years ago, a blink in cosmic time. The bubbles force us to confront an uncomfortable truth. Our galaxy isn't some static backdrop. It's alive, dynamic, and capable of eruptions that dwarf anything we've ever witnessed. This realization reshapes how we see ourselves. We're not just inhabitants of a quiet spiral arm, we're witnesses to an ongoing cosmic drama. The same forces that carved the Fermi bubbles could one day influence our corner of the galaxy, whether through shock waves, radiation, or other phenomena we haven't even discovered yet. It's a reminder that Earth isn't as isolated as we might like to think, yet there's beauty in this uncertainty. The bubbles show us that science isn't about having all the answers, it's about asking better questions. Every time we solve one mystery, like the origin of these structures, we uncover 10 more. And that's what makes the universe so exhilarating. We're part of a species brave enough to stare into the abyss, to measure the immeasurable, and to keep searching even when the scale of our ignorance feels overwhelming. In a way, the Fermi bubbles are the perfect metaphor for human curiosity. They're vast, enigmatic, and invisible to the naked eye, yet once we knew to look, they transformed how we see everything. That's the power of science. It doesn't just reveal the universe's secrets. It reminds us that wonder is endless, and our journey to understand it has only just begun. Now, let's take this cosmic puzzle a step closer to home. Could these immense Fermi bubbles have left their mark not just on our galaxy, but on Earth itself? It's a fascinating thought, one that bridges the gap between distant astrophysics and the very air we breathe. Picture this: around 2 to 4 million years ago, when the bubbles were likely forming, Earth was in the Pliocene epoch, a time of relative warmth with early hominids just beginning to walk the planet. If the Fermi bubbles were born from a violent outburst of our galaxy's supermassive black hole, the energy released would have been unimaginable. Some scientists speculate that such an event might have sent high-energy particles racing through the Milky Way, potentially reaching our solar system. What would that mean for Earth? While the bubbles themselves are tens of thousands of light years away, their creation could have had subtle, cascading effects. Increased cosmic rays bombarding our atmosphere might have influenced cloud formation, potentially altering climate patterns. There's even research suggesting that such particle showers could have affected the ozone layer, though the evidence remains speculative. Here's where it gets even more intriguing. Geological records from that era show shifts in climate and minor extinction events. Could there be a connection? It's a stretch, but not impossible. The universe is full of invisible threads linking the grandest scales to the most intimate details of life. Of course, we're venturing into the realm of what if. The truth is, we don't yet have concrete proof tying the Fermi bubbles to Earth's history. But that's the thrill of science, asking bold questions and following the clues, no matter where they lead. Whether these galactic giants left a fingerprint on our planet or not, they remind us that Earth doesn't exist in isolation. We're part of a dynamic, interconnected cosmos, where even the most distant events might whisper echoes in our own backyard. Now, let's shift our focus to the hurdles scientists face when bringing these cosmic giants down to Earth, literally. Explaining structures as vast and abstract as the Fermi bubbles to the public isn't just about simplifying the science. It's about translating the unimaginable into something relatable without losing the awe-inspiring scale of the phenomenon. Think about it. How do you describe an object 50,000 light-years tall to someone who's never left their hometown? Or convey the energy of 100,000 supernova to an audience more familiar with household electricity bills? The challenge lies in bridging that gap between cosmic enormity and human-scale understanding. One common stumbling block is the sheer timescale involved. When we say the bubbles formed 2 to 4 million years ago, that number often glazes eyes rather than sparks curiosity. To put it in perspective, imagine stacking every human lifetime since the dawn of Homo sapiens. That's roughly the time frame we're talking about. Yet even this analogy barely scratches the surface of deep time. Then there's the invisible nature of the bubbles themselves. Unlike planets or nebulae, you can't point a backyard telescope at them. Their gamma-ray emissions are invisible to human eyes, requiring detectors in space just to glimpse them. This makes it harder for the public to connect emotionally with something they can't see or visualize easily. Scientists also grapple with balancing accuracy and simplicity. Oversimplify and you risk spreading misconceptions. Overcomplicate and you lose your audience. Take the term bubbles itself. While handy shorthand, it misleadingly suggests something fragile and ephemeral, not these resilient, energy-packed structures. Perhaps the biggest hurdle is conveying why any of this matters. To the average person, galactic structures light years away might seem irrelevant to daily life. The trick is highlighting those unexpected connections, like how studying these bubbles helps us understand Earth's place in a violent universe, or how their energy processes mirror scaled-up versions of particle accelerators in labs. Yet despite these challenges, the effort pays off. When someone grasps that our Milky Way isn't some static painting but a dynamic, ever-changing arena with Fermi bubbles as its latest masterpiece, that moment of understanding is what makes science communication worth every struggle. Now, let's pull back the curtain on another layer of this cosmic puzzle, the real-world challenge of funding and research priorities. Studying the Fermi bubbles isn't just about scientific curiosity. It's a high-stakes balancing act where every telescope hour and research grant counts. Astrophysics is a field bursting with mysteries, from dark matter to exoplanets, each vying for attention and resources. When it comes to allocating limited funding, bubble research has to compete with projects that might seem more immediately tangible, like hunting for habitable planets or tracking near-Earth asteroids. The question isn't just about what we study, but what gets prioritized in a landscape where every dollar and minute of observation time is precious. One hurdle is the sheer specialization required. Unlike broader topics like black holes or supernova, Fermi bubbles demand niche expertise in gamma-ray astronomy and galactic dynamics. This means fewer researchers are equipped to dive deep, which can sway funding committees toward more mainstream areas with larger pools of talent. Yet, the bubble's uniqueness is precisely what makes them invaluable. They're a window into extreme galactic processes we can't study anywhere else. Then there's the instrumentation challenge. Capturing high-quality data on the bubbles requires cutting-edge telescopes, some of which weren't even designed with these structures in mind. Repurposing equipment or lobbying for new instruments takes years of advocacy and convincing budget holders that the investment will pay off. It's a bit like asking someone to fund a microscope when they're more familiar with telescopes. You have to prove the tool will reveal something revolutionary. But here's the twist: the competition isn't just with other astrophysics projects. It's also with public perception. Funding often follows public interest, and let's face it, gamma-ray bubbles 50,000 light-years tall don't exactly trend on social media. Scientists have to articulate not just the how of their research, but the why in ways that resonate with policymakers and taxpayers. Whether it's drawing parallels to Earth's climate or highlighting the tech spin-offs from gamma-ray detection, connecting the cosmic to the everyday is key. Despite these hurdles, the tide might be turning. As simulations improve and telescopes like the upcoming Cherenkov array come online, the case for bubble research grows stronger. Every new piece of data could be the clue that cracks the mystery, and that's a gamble more institutions are willing to take. After all, understanding these galactic giants isn't just about solving a puzzle, it's about rewriting the story of our own Milky Way. Now, let's take a journey across the globe to see how scientists are joining forces to crack the Fermi Bubbles mystery. This isn't a solo mission, it's a worldwide effort with researchers from different continents pooling their expertise and resources to tackle one of the galaxy's biggest enigmas. In the United States, teams at NASA and universities like Harvard and Stanford are analyzing data from the Fermi Gamma-Ray Space Telescope, piecing together the bubble's high-energy emissions. Meanwhile, over in Europe, the Max Planck Institute in Germany and the University of Cambridge in the UK are leading the charge with advanced simulations, testing how black hole outbursts or star formation could have sculpted these colossal structures. Down under, Australian astronomers are using the Parkes radio telescope to study the bubble's interaction with the Milky Way's magnetic fields. And in Japan, researchers at the University of Tokyo are collaborating with NASA to cross-check findings from different wavelengths, ensuring no clue goes unnoticed. But perhaps the most exciting part is how these teams bridge distances. Through virtual conferences and shared databases, a scientist in Chile can instantly access observations from a telescope in South Africa, while a theorist in France tweaks a simulation based on fresh data from Argentina. It's a real-time, global brainstorming session where every time zone contributes a piece of the puzzle. What makes these collaborations so powerful is their diversity of perspective. An astrophysicist trained in gamma-ray astronomy might spot something a radio specialist misses, and vice versa. By combining their strengths, these international teams are doing more than just sharing data. They're building a fuller, richer understanding of the Fermi bubbles than any single group could achieve alone. And this spirit of cooperation is only growing. Upcoming projects like the Cherenkov telescope array spanning 3 continents promise to deepen these partnerships even further. Because when it comes to unraveling the secrets of our galaxy, the best tool we have isn't just a telescope, it's teamwork. Now, let's shift gears and talk about how you can get involved in uncovering the secrets of the Fermi bubbles. You don't need a PhD or access to a multi-million-dollar telescope to contribute to this cosmic detective work. Thanks to publicly available data and citizen science projects, amateur astronomers and curious minds can play a role in piecing together this galactic puzzle. Start by exploring data from the Fermi Gamma-Ray Space Telescope, which is freely accessible through NASA online archives. Websites like the Fermi Science Support Center provide tools to visualize gamma-ray emissions, allowing you to scan the regions above and below the Milky Way center for signs of the bubble's high-energy glow. Look for symmetrical, lobe-like structures stretching tens of thousands of light years. These are the telltale fingerprints of the Fermi bubbles. If gamma rays feel a bit too intense, radio astronomy offers another window. Platforms like the Skyview Virtual Observatory let you overlay observations from different telescopes, comparing radio waves with gamma-ray maps to see how the bubbles interact with the galaxy's magnetic fields. You might even spot the faint, diffuse haze connecting the bubbles to the galactic disk, a clue scientists are still trying to decode. For those who love hands-on projects, citizen science initiatives like Zooniverse often feature tasks related to galactic phenomena. By classifying data or flagging unusual patterns, you could help researchers identify new features or confirm existing theories about the bubble's structure. Every pair of eyes counts, and sometimes a fresh perspective from an amateur can spot something professionals might overlook. And don't forget social media. Astronomy communities on platforms like Twitter and Reddit frequently share tips, findings, and even tutorials on how to process telescope data at home. Join the conversation, ask questions, and who knows, you might be the next to uncover a piece of the Fermi Bubbles mystery. The universe isn't just for the experts, it's for anyone willing to look up and wonder. So grab your laptop, dive into the data, and who knows what cosmic secrets you might help reveal. Now imagine stepping inside the Fermi Bubbles themselves, not with a telescope but through the power of virtual reality. Scientists are using cutting-edge VR simulations to explore these colossal structures in ways traditional observations simply can't match. Picture slipping on a headset and suddenly floating amidst the gamma-ray glow, tracing the bubbles' intricate edges or diving deep into their mysterious heart. These immersive simulations aren't just for show. They're helping researchers visualize complex data in 3 dimensions, revealing patterns and connections that flat images might miss. By flying through the bubbles, astronomers can study their structure up close, testing theories about how they formed and what keeps them inflated. For example, VR lets scientists manipulate magnetic field lines or simulate particle flows, offering clues about the bubble's energy sources. Some teams are even collaborating with game developers to create interactive experiences. Imagine controlling a virtual spaceship, weaving between the bubble's towering walls while collecting data on their temperature or density. These playful approaches aren't just engaging, they're sparking new ideas. A scientist might notice an odd asymmetry or an unexpected hotspot during a VR session, leading to fresh hypotheses. Universities and labs are starting to share these tools publicly so you can explore the bubbles from home. Platforms like NASA's Eyes on the Solar System are expanding to include galactic-scale phenomena, putting cosmic wonders like the Fermi Bubbles at your fingertips. Whether you're a researcher or just curious, VR is turning distant mysteries into something you can almost reach out and touch. And here's the thrilling part: as VR technology improves, so will our ability to unravel the bubble's secrets. Future simulations might incorporate real-time data from telescopes, letting you watch as new observations reshape our virtual models. The line between scientist and explorer is blurring, and the Fermi Bubbles are waiting. Now let's shift our gaze to another cosmic frontier: gravitational waves. These ripples in space-time, first detected in 2015, have opened a new window into the universe's most violent events. Could they also hold clues about the Fermi Bubbles? Some scientists are beginning to wonder if ancient black hole mergers, the kind that send gravitational waves echoing across the cosmos, might have played a role in shaping these mysterious structures. Imagine a scenario millions of years ago when Sagittarius, a star, the supermassive black hole at our galaxy's center, devoured a smaller black hole or neutron star. The colossal energy released in such a merger could have sent shock waves through the surrounding gas, potentially inflating the bubbles we see today. While we haven't yet detected gravitational waves from events this old, next-generation observatories like the Laser Interferometer Space Antenna, or LISA, could change that. LISA, set to launch in the 2030s, will be sensitive to low-frequency gravitational waves, the kind produced by supermassive black hole mergers. If it picks up signals that align with the Fermi Bubble's estimated age, it could strengthen the case for a black hole outburst as their origin. Even more intriguing, subtle distortions in the gravitational wave signals might reveal how such an event interacted with the galaxy's gas, leaving behind the bubble's distinctive shape. Of course, this idea is still speculative. Gravitational wave astronomy is young, and linking specific waves to structures as vast as the Fermi Bubbles would be a monumental challenge. But that's what makes it exciting. Each new detector brings us closer to testing these bold hypotheses, peeling back another layer of the universe's secrets. And here's the bigger picture. If gravitational waves do connect to the bubbles, it would mean these enigmatic structures aren't just a local mystery. They'd be part of a cosmic story written in spacetime itself, one where black holes don't just lurk silently, they reshape galaxies. As we wait for LISA and other detectors to come online, one thing is certain: the Fermi Bubbles still have surprises in store. Now let's take a step beyond our own galaxy and consider what the Fermi Bubbles might mean for planets orbiting stars in distant corners of the universe. If structures like these exist in other galaxies, and there's growing evidence that they do, they could play a surprising role in shaping the habitability of exoplanets. Picture a star system nestled near the core of another galaxy, where enormous bubbles of high-energy radiation stretch into space. The intense gamma rays and cosmic rays pouring out of these structures could strip away atmospheres, bombard surfaces with radiation, and even alter the chemistry of potential oceans. For any life forms trying to emerge on planets in these regions, the environment might be far harsher than anything we experience in the Milky Way's quieter suburbs. But it's not all doom and gloom. Some scientists speculate that these energetic processes could also have unexpected benefits. The same radiation that threatens life might also trigger chemical reactions in a planet's atmosphere, creating complex molecules that serve as the building blocks for biology. In other words, while the bubbles could sterilize some worlds, they might also set the stage for life to arise in others. Then there's the question of timing. Fermi-like bubbles are thought to be relatively short-lived on cosmic scales, lasting perhaps a few million years. That means a planet's habitability could change dramatically depending on whether it's caught in the crossfire during a bubble's active phase or enjoys the calm that follows. A world that's uninhabitable today might have been a thriving oasis millions of years earlier, or vice versa. This raises a fascinating possibility. If we're searching for life beyond our solar system, maybe we should pay special attention to galaxies without these enormous structures. Or perhaps we should look for planets that orbit stars at just the right distance, close enough to benefit from the bubble's chemical effects, but far enough to avoid their worst radiation. Either way, the Fermi Bubbles remind us that habitability isn't just about a planet's composition or its star. It's also about the galaxy it calls home. As telescopes like the James Webb Space Telescope peer deeper into other galaxies, they might soon spot more of these bubble-like structures, and when they do, we'll have to rethink what it really takes for a planet to support life in a universe full of cosmic fireworks. Now, let's shift our focus to how cutting-edge technology is revolutionizing our understanding of the Fermi Bubbles. Artificial intelligence is stepping into the cosmic spotlight, helping scientists sift through mountains of data to uncover hidden patterns in these mysterious structures. Machine learning algorithms are particularly well suited for this challenge. With the Fermi Bubbles emitting radiation across multiple wavelengths, the datasets are enormous and complex. Traditional analysis methods would take researchers years to process, but AI can identify subtle correlations and anomalies in a fraction of the time. These algorithms excel at spotting faint signals buried in the noise, whether it's a peculiar gamma-ray fluctuation or an unexpected distribution of high-energy particles. One exciting application involves neural networks trained to map the bubble's intricate structure. By feeding these systems observations from telescopes like Fermi and Chandra, scientists can reconstruct the three-dimensional shape of the bubbles with unprecedented precision. This helps answer questions about their symmetry, density variations, and how they interact with the surrounding galactic environment. Another breakthrough comes from unsupervised learning techniques. Without being told what to look for, these AI systems can detect previously unnoticed features in the data. For instance, they might reveal pockets of unusually high energy radiation or unexpected connections between the bubbles and other galactic phenomena. These discoveries often lead to new hypotheses that human researchers might have missed. The beauty of this approach lies in its adaptability. As new telescope data pours in from gamma-ray observatories, radio telescopes, and future missions, the machine learning models continuously refine their understanding. They're not replacing human scientists, but supercharging their ability to ask better questions and test theories faster than ever before. What's next? Researchers are now developing AI tools to simulate the bubble's formation under different scenarios. By combining machine learning with astrophysical models, they hope to pinpoint which energetic events could have created these colossal structures. It's a powerful reminder that solving cosmic mysteries often requires both the intuition of human minds and the brute force pattern recognition of artificial intelligence. Now, let's clear up some of the confusion surrounding the Fermi bubbles. Despite their enormous size and energetic nature, these structures aren't the cosmic threat some might imagine. One common misconception is that the bubbles pose a danger to Earth, like a galactic-scale explosion heading our way, but the reality is far less dramatic. The bubbles are located tens of thousands of light-years away from us, and their high-energy emissions are spread so thinly across such vast distances that they have no measurable effect on our planet. Another misunderstanding is that the bubbles are a recent phenomenon, something actively changing or expanding right now. In truth, these structures are likely millions of years old, a remnant of some ancient cataclysm near the Milky Way center. While they are still fascinating to study, they're not some sudden, unfolding event, just a slow-moving echo of the galaxy's violent past. Some people also assume the bubbles are solid structures like giant walls in space. But they are actually diffuse clouds of hot gas and high-energy particles, more like a faint, glowing fog than anything with a defined surface. Their sharp edges in telescope images come from the way they emit radiation, not because they have physical boundaries like a soap bubble. Then there's the idea that the bubbles are unique to our galaxy. While they're certainly extraordinary, similar structures have been spotted in other galaxies, suggesting they might be a common byproduct of supermassive black hole activity or intense star formation. The Fermi bubbles aren't an anomaly, they're part of a broader cosmic story. Finally, let's tackle the myth that studying them requires impossibly advanced technology. While cutting-edge tools like AI and space telescopes help, amateur astronomers can even contribute by analyzing public data from missions like Fermi. The bubbles aren't just for professional scientists, they're a reminder that the universe invites curiosity from everyone. So, while the Fermi bubbles are mysterious and awe-inspiring, they're not something to fear or misunderstand. They're a natural part of our galaxy's history, waiting to reveal their secrets to anyone willing to look closer. Now, let's take a moment to appreciate how the Fermi bubbles have inspired a unique fusion of art and science. These colossal structures aren't just fascinating to researchers, they've also captured the imagination of artists, leading to breathtaking collaborations that bring cosmic mysteries to life. Scientists and visual artists often work together to translate complex data into stunning images and animations, helping the public grasp the scale and beauty of these enigmatic features. One remarkable example is the way digital artists use telescope observations to create immersive visualizations of the bubbles. By combining gamma-ray data with artistic interpretation, they produce vibrant renderings that show the bubbles' vast, hourglass-like shapes stretching above and below the Milky Way. These visuals aren't just eye-catching, they serve a crucial purpose, making abstract astrophysical concepts tangible and relatable. Museums and planetariums have also embraced these collaborations, featuring interactive exhibits that let visitors fly through the bubbles in virtual reality. Imagine putting on a headset and soaring past towering waves of high-energy particles, gaining a visceral sense of their enormity. These experiences bridge the gap between scientific discovery and public wonder, proving that art can be a powerful tool for education. Even traditional mediums like painting and sculpture have been influenced by the bubbles. Artists draw inspiration from their symmetrical forms and energetic glow, creating works that blend scientific accuracy with creative expression. Some pieces even incorporate real data, like spectral colors representing different energy levels of gamma rays, turning raw numbers into visual poetry. These collaborations remind us that science doesn't exist in a vacuum. By merging the precision of astrophysics with the creativity of art, we gain new ways to explore and appreciate the universe's wonders. Whether through a VR headset or a gallery wall, the Fermi bubbles continue to spark curiosity, not just as objects of study, but as sources of inspiration. Turning our attention to the next generation of scientists, let's explore how students can dive into Fermi bubble research firsthand. For undergraduates eager to study these cosmic structures, there are more opportunities than you might think. Many universities collaborate with space agencies, offering research assistant positions where students help analyze gamma-ray data or run simulations of the bubble's formation. A great starting point is NASA's Fermi Guest Investigator program, which welcomes student proposals to study the bubbles using telescope data. Imagine contributing to real astrophysical research as an undergrad. Your work could even end up in published papers. Some students focus on coding, developing algorithms to map the bubble's gamma-ray emissions, while others assist in modeling how black hole outbursts might have created these colossal features. Summer research programs are another fantastic pathway. Institutions like the National Science Foundation's research experiences for undergraduates often include astrophysics projects related to galactic structures. Picture spending your summer at an observatory processing data from telescopes that peer into the heart of the Milky Way. Even without a formal program, undergrads can get involved through citizen science initiatives. Platforms like Zooniverse host projects where students classify gamma-ray signals, helping professionals identify patterns in the bubble's emissions. And for those with a passion for outreach, there's always a need for science communicators who can translate bubble research into engaging content for the public. The key takeaway: you don't need a PhD to start exploring the Fermi bubbles. With curiosity and initiative, undergraduates can already play a role in unraveling one of the galaxy's most captivating mysteries. Who knows, your work today might shape tomorrow's breakthroughs. Now let's shift our gaze from research labs to the silver screen, where the Fermi bubbles have sparked their own kind of cosmic creativity. While these colossal structures might not be household names just yet, they've begun making subtle appearances in science fiction and documentaries, often serving as backdrops for grand cosmic mysteries. Take the documentary Journey to the Edge of the Universe, for example. While it doesn't focus solely on the bubbles, it beautifully visualizes their scale, using cutting-edge animations to show how they tower over the Milky Way. The film treats them like silent giants, emphasizing how much we still don't understand about our own galaxy. Science fiction has also flirted with the bubble's potential. In the TV series The Expanse, though never named directly, similar structures appear in distant galaxies, hinting at ancient black hole activity. It's a clever nod to real astrophysics, weaving the Fermi bubble's mystery into speculative storytelling. Even video games like Elite Dangerous incorporate bubble-like anomalies, letting players explore regions inspired by these enigmatic formations. But perhaps the most striking portrayal comes from Cosmos, Possible Worlds, where Neil deGrasse Tyson uses the bubbles to illustrate how dynamic and violent our galaxy's core can be. The show's vivid animations make the invisible gamma rays tangible, helping audiences grasp why these structures fascinate scientists. What's interesting is how media often amplifies the bubble's drama, casting them as cosmic time capsules or remnants of galactic catastrophes. While artistic license takes over, these portrayals do something vital. They translate complex science into wonder, sparking curiosity in viewers who might never open an astrophysics journal. So next time you spot a glowing hourglass shape in a sci-fi scene, you'll know it might just be our very own Fermi bubbles whispering their secrets to the stars. Now let's step back from the cosmic scale for a moment and find simpler ways to picture these enormous structures. Imagine the Fermi bubbles as a pair of giant balloons slowly inflating from the center of our galaxy. But instead of air, they're filled with invisible energy, like holding your hand near a hot stove and feeling the heat without seeing the flames. That's how these bubbles emit gamma rays, detectable only with special instruments. Another way to think about them is like a galactic sneeze. Picture Sagittarius A, the supermassive black hole at the Milky Way's heart, having a cosmic outburst blasting material outward in two opposite directions. The bubbles are the lingering echo of that explosive event, frozen in space for millions of years. For something more familiar, consider a lava lamp. The blobs rising and falling inside it mimic how energy might have surged from the galactic center, creating these symmetrical lobes. Or think of the Milky Way as a spinning top, and the bubbles as the shimmering glow around its edges when light catches it just right. Even weather patterns on Earth offer a useful comparison. The bubbles behave like a massive storm system with turbulent edges and high-energy winds racing through them. But instead of rain and lightning, this storm produces gamma rays and cosmic particles. The key takeaway: while the Fermi bubbles are unimaginably vast, everyday analogies help bridge the gap between their cosmic scale and our human experience. Whether it's balloons, sneezes, or lava lamps, these comparisons remind us that the universe operates by rules we can recognize just on a far grander stage. Now, let's zoom out and consider how studying the Fermi bubbles fits into the bigger picture of unraveling the Milky Way story. These colossal structures aren't just cosmic oddities, they're like missing puzzle pieces in our understanding of galactic evolution. By analyzing their origins and behavior, scientists can trace back violent events that shaped our galaxy millions of years ago, much like geologists study rock layers to uncover Earth's history. What makes bubble research so groundbreaking is how it connects disparate fields of astronomy. The energy required to create them hints at past cataclysms near Sagittarius A, offering clues about how supermassive black holes influence their host galaxies over time. Simultaneously, the bubble's chemical composition and structure provide a snapshot of how our galaxy processes matter and energy on the largest scales. Looking ahead, advancements in telescope technology promise to reveal even more. Upcoming instruments capable of peering deeper into gamma-ray and X-ray emissions could detect fainter features within the bubbles, potentially uncovering older, nested structures from previous outbursts. This would be like finding tree rings inside the bubbles, each layer marking a different era of galactic activity. Moreover, comparing the Fermi bubbles to similar structures in other galaxies helps astrophysicists identify universal patterns. If multiple galaxies show evidence of these energetic outflows, it could mean they're a common phase in galactic life cycles, perhaps tied to periods when black holes wake up and reshape their surroundings. Ultimately, every discovery about the bubbles refines our models of how galaxies grow and change. They challenge us to rethink assumptions, from how black holes feed to how galaxies distribute heavy elements into intergalactic space. As research continues, the Fermi bubbles may well become a cornerstone in our quest to decode the Milky Way's past and predict its future. Now, shifting our perspective slightly, let's consider the human side of this cosmic mystery. Communicating the science behind the Fermi bubbles comes with unique ethical challenges. These structures are still poorly understood, and scientists must balance excitement with caution when sharing discoveries. Overstating what we know could mislead the public, while downplaying their significance might stifle interest in groundbreaking research. One key responsibility is transparency. Researchers must clearly distinguish between established facts and educated guesses. For example, while we know the bubbles emit gamma rays, their exact origins remain theoretical. Presenting hypotheses as definitive truths could erode trust in science, especially when new data inevitably reshapes our understanding. Another consideration is accessibility. The scale and complexity of the Fermi bubbles can feel overwhelming, So scientists and science communicators have a duty to translate these concepts without oversimplifying. Analogies like comparing the bubbles to galactic exhaust fumes from a black hole's past activity help bridge the gap without sacrificing accuracy. There's also the question of public impact. When discussing cosmic phenomena, it's easy to sensationalize headlines like suggesting the bubbles pose a threat to Earth. Responsible communication means addressing such fears head-on, clarifying that these structures are distant and pose no danger while still highlighting their scientific importance. Ultimately, ethical science communication fosters curiosity without feeding misinformation. By embracing uncertainty as part of the process, we invite the public to join the journey of discovery, where every new observation, whether it confirms or contradicts our ideas, brings us closer to understanding our galaxy's dynamic history. Turning now to the human element behind these cosmic discoveries, let's hear from the astronomers whose lives have been profoundly shaped by the Fermi bubbles. One researcher recalls the moment the first gamma-ray data flashed across their screen, a rush of excitement mixed with disbelief. They'd spent years studying black holes, but nothing prepared them for the scale of these structures. Overnight, their career pivoted, and they found themselves at the forefront of a mystery that could redefine our understanding of the Milky Way. Another scientist shares how the bubbles became their obsession. They describe late nights poring over simulations, tweaking variables to recreate the bubble's sharp edges. At one point, they even dreamed about gamma-ray patterns. What kept them going was the thrill of chasing something no one had ever explained. A puzzle that demanded creativity and patience in equal measure. Then there's the story of a young graduate student who stumbled onto an unexpected connection between the bubbles and ancient star-forming regions. Their accidental discovery, initially dismissed as noise in the data, eventually led to a groundbreaking paper. For them, the bubbles were a reminder that science often rewards those who question assumptions. These personal stories highlight something bigger than the science itself, the passion and perseverance driving it. Whether it's the veteran astronomer who rededicated their career or the newcomer who saw a chance to make their mark, the Fermi bubbles have a way of igniting curiosity that lasts a lifetime. And as we'll see next, that curiosity is fueling tools that let anyone explore these mysteries firsthand. Now let's step into the digital realm, where cutting-edge tools bring the Fermi bubbles right to your fingertips. Imagine being able to explore these colossal structures from the comfort of your home, no telescope required. Thanks to platforms like the Fermi Science Support Center, anyone with an internet connection can dive into the same gamma-ray data that astronomers use. Their interactive sky maps let you pan across the Milky Way, highlighting the bubble's intense emissions in vivid detail. For those who prefer a more hands-on approach, apps like Space Engine take things even further. This virtual universe simulator allows you to fly through a scaled model of our galaxy, passing straight through the Fermi bubbles as if you were a cosmic traveler. You can adjust angles, zoom in on their razor-sharp edges, and even compare them to other galactic structures, all while learning about the science behind their formation. Then there's Zooniverse, a citizen science hub where amateur astronomers contribute to real research. One of their projects focuses on classifying gamma-ray patterns, helping scientists pinpoint anomalies in the bubble's structure. It's a chance to be part of the discovery process, with tutorials that guide you through analyzing data like a pro. And don't overlook the power of simple yet powerful tools like Aladdin Light. This browser-based sky atlas overlays data from multiple telescopes, letting you switch between gamma-ray, X-ray, and microwave views of the bubbles. Seeing how different wavelengths reveal different features drives home just how complex these structures truly are. What makes these tools so exciting is how they blur the line between scientists and the public. Whether you're a student, a space enthusiast, or just curious, you're now equipped to uncover secrets of the universe that were once reserved for researchers with billion-dollar telescopes. And as we'll see next, this spirit of exploration is pushing the boundaries of how we visualize cosmic mysteries. As we bring our journey through the cosmos to a close, let's take a moment to reflect on the sheer enormity of the Fermi Bubbles. These towering structures, stretching 50,000 light-years above and below our galaxy, are a humbling reminder of just how much we have yet to understand about the universe. They challenge everything we thought we knew about the Milky Way, from the behavior of supermassive black holes to the invisible dance of dark matter. Yet for all we've uncovered, the bubbles remain one of astronomy's greatest puzzles. Are they the echoes of a violent outburst from Sagittarius, a star, the aftermath of a frenzied burst of star formation? Or could they be evidence of something even more exotic, like particles of dark matter annihilating in the heart of our galaxy? The answers are still out there, waiting to be discovered by the next generation of telescopes and the curious minds who operate them. What's truly exciting is that this story is far from over. Every new observation, every advanced simulation, and every citizen scientist's contribution brings us closer to unraveling the mystery. The Fermi Bubbles aren't just a scientific curiosity, they're a gateway to rewriting the rules of galactic physics. And who knows, the key to understanding them might already be hidden in data we've yet to analyze, or in an idea waiting to be sparked by someone watching this very video. So keep looking up, stay curious, and never stop asking questions. The universe is full of wonders like the Fermi Bubbles, reminding us that there's always more to explore, more to learn, and more to marvel at. If you enjoyed this deep dive into the unknown, don't forget to hit that like button, subscribe for more cosmic adventures, and ring the notification bell so you never miss out on the next big discovery. Until then, keep wondering, because the next great mystery of the cosmos could be revealed any